Okay, this is the last lecture from section 4, basically the FinFET and some of its processing. The FinFET was invented by Who's group at Berkeley in the 90s. So who invented the FinFET? That's my question. There's a schematic of the FinFET. You can see it looks completely different than our planar device, and a few things are going to be still familiar: our source, our gate, and our drain, but a few things are a little bit different, like how we might think of the length and what we might think of the width. So this is a cross section, let's say, through the middle of this thing, and basically it helps us identify what we're associating with the width of the device. So in this particular case, it's going to be related to the height of the fin and the width of the fin, which may be augmented by the fact that there's a thin oxide layer there, but these are sort of details that we're not going to worry about. We're just going to think of the width of the device being the 2 times the height plus the width of the silicon. Here's a comparison with the planar MOSFET. In this case, I've tried to just outline that the drain is on this side, the source is on this side, and this is the previous width, and that was our our gate dielectric is that yellow under there, and this is the length. So that's our familiar W over L kind of ratios that we looked at when we were talking about the device characteristics. Over here it's the same idea. This sort of becomes the source side, this is the drain side, and this becomes the gate, and this is the channel. And 3 arrows are shown here indicating that current can flow on those 3 surfaces, 2 related to the height and 1 related to the width. And again, it's a fully depleted device, which means that there's no mobile carriers when the device is off. Here's some variations on it. Here's again our planar fully depleted SOI. So that was our, again, a fully depleted device, which is silicon and insulator. So this would be the insulator layer shown down here. And we'd have, let's say for an NFET, the source and the drain, and then our gate that we're familiar with. And there's a maybe more clear illustration of that. Now here's the FinFET, silicon on oxide. Again, this is drawn similar to the previous page. This particular example is one that is grown on this buried oxide layer, and this is then the fin height and the fin width. So one side would be the source, one side the drain, and then the gate would be this U-shaped region. Similarly, for the case where it's grown in bulk, this particular case, we have these silicon trench isolations, and we looked at a few slides back how that was implemented. So anyway, here's the formation of a FinFET. In this particular case, there would have been that buried oxide that was created in the silicon. Remember, there's silicon underneath this here, bulk silicon. That buried oxide would have been created from an ion implantation layer, leaving some silicon on top, and then it gets basically etched away, leaving the fin. In which case then source and drain can be grown and patterned, and basically this would form our source, our drain, and this will be our gate region. So some other processing takes place. There's a nitride spacer. Don't know the exact reasons for it, but this is the place where the gate material, let's say a P-type, P+ polysilicon germanium compound, would have been grown here. So that's basically how, one means of creating a FinFET maybe. This is a side view of it. Again, we're looking at the fin. In this particular case, the width of the silicon is denoted here, and these are the heights of the fin. And in this particular case, since it has a hard mask up top here, the only surfaces that would conduct the current are along the sides here. So our fin height would be related to the device width from before, and basically the device width is going to be twice the height. And here's a photomicrograph of a cross section of a fin that's actually been deposited, and this is sort of a zoomed in region of that. And then we're going to look at this little section here, and you can sort of see this would be the silicon, this would be the thickness of the oxide layer, and then this would be the gate material. So Intel's Tri-Gate, it's a 22 nanometer process, currently coming online in a number of places in 2013. The Tri stood for current on both the sides as well as the top conducting surface. So the Tri-Gate had some benefits: dramatic performance at low operating voltage, better than bulk or that partially depleted silicon oxide or silicon on insulator, or the fully depleted planar silicon on oxide devices. So as we'll see in a slide or two, 37% performance increase at low voltage and a 50% power reduction with the similar performance. So it has improved switching characteristics, means that it's easier to differentiate between on current and off current, and has higher drive for given transistor footprint. And the other thing that's quite important, it's only a few percent cost adder to the fabrication process of bulk CMOS of our planar devices. So here's a performance curve that was taken from somewhere on Intel. Basically delay, which is this normalized or nominal delay. And at low voltages, it's 37% faster than the planar device, and even at higher voltages, still 18% faster. So there's certainly some advantages of the FinFET technology. Here's again a photomicrograph of a slice. So this is the fin itself, and this would be the gate over top of it. So basically the gate is going to enhance this region in here to put some carriers, and the source and drain would be either in to the plane or out of the plane. And here's the zoomed in region of it, where you can clearly see the silicon, you can clearly see the oxide layer, and then you can see the gate material. This is in a lot more detail. You can get an appreciation for how much material processing goes in here. This was the silicon fin, which was grown and etched away, and basically the fin remains, and then there's a silicon oxide dielectric, which is 1.1 nanometer. There was a hafnium high K dielectric, which is basically another nanometer. And then there was titanium nitride work function metal here, which basically allowed you to connect up the aluminum to the silicon more easily, and for electrical reasons as well. There was also a titanium nitrogen barrier. Don't know the purpose of that. And then the titanium aluminum NMOS work function metal, or basically our gate itself out here. So lots of material processing going into building one of these devices. Here's some more pictures of the Intel 22 nanometer fin. There's a couple of varieties of them. One was a high speed, low power. The other was a high voltage. Just look at this one, for example. It's clear that we can identify the cross section of the fin here. And so when we look over here, we can see multiple fins, which would be running in this direction here. So basically, it's as if when you put them in this fashion, it's as if you're increasing the width or the drive of the device. In this middle picture, it's very difficult to see where the fin is. It might be a cross section, let's say through here, don't know for sure, and it's more like finding Waldo if you zoom in and try to look for the fin there. Anyway, here's a picture of Intel's Tri-Gate again, some of the lower levels and some of the devices connected up. Very difficult to sort of recognize anything at all, but you can probably appreciate that these things here would represent the fins and these things would be gates. Here's Intel's Tri-Gate SRAM. Again, this was taken apart by a company called Chipworks, which basically reverse engineers the layouts. And this is our old friend, our old SRAM. And we can recognize a couple things in here. Cross-couple latch that holds the state, and then an ability to interrogate it or to write new data onto it, the bit line and the bit bar line. And then our word line, which strobes these two NMOS transistors. So these 6 transistors here are represented by the 6 transistors, which are FinFETs in here, and they were kind enough to at least label all the inputs as the bit line and the bit line bar and the word line, VSS and VDD. So sort of now here's a roadmap beyond bulk CMOS. I think it came from the mid let's say 2005-ish or so. Here's a more up-to-date version, which was 2009. The slides kind of look the same. The only thing that's kind of missing here that we'd be somewhat familiar with would be sort of saying, where's the FinFET? And we could probably draw it in right here and pencil it in. But this is our evolution, our familiar bulk CMOS process. We went through looking at some silicon and insulator to our fully depleted silicon and insulator. We looked at the high K gate dielectric so that you can make the gate thicker and it would look electrically thin. The metal gate, where we basically ended up replacing the polysilicon and making a metal gate device to make it gain faster and improve the connectivity of the device. And then there's some technologies that are represented here as being in the future. One is a single electron transistor. One is this 3D heterogeneous integration, which just means different types of devices connected up. So these would be layers of silicon, probably processed individually and then assembled after the fact. Certainly there is 2.x integration, but whether it'll ever be fully 3D is very difficult to say. And there are some other very gray areas here, sort of the quantum dot and some, I think the other one was this nanotube kind of technology. So where these are going to show up in the future is going to be hard to say, but certainly they may show up somewhere. And that's all for this section.